Ed in New York, too.
We are
Good
recording.
evening,
Marty, it's all yours.
everyone. This is Marty Feldman, Chair of the New England section, here for our March meeting, which is going to be a revisit of something we touched on in the spring, I believe, and I'm getting the years mixed up, but it was some spring for ATSC 3, which was kind of sluggishly rolling along at the time, but has really picked up speed. And I think you're going to find some interesting developments in that. To cover that is Dave Folsom from Pearl. And Dave was a retired Chief Technology Officer for Raycom Media, which is now part of Gray. And he is fortunately up to speed on this and is going to give you plenty of information of where we all are in this transition. There are actually many TV stations, I understand, that are actually ready to send the ATSC3 over the air. Now all we need is some televisions. I especially want to thank Cheryl Lustenberger of WGBH, one of the PBS flagship stations, who is one of our managers and put this meeting together. And it was a lot of work, and I really want to thank you, Cheryl. And now I want to turn it over to you to give us a little bit more of information on Dave and get the meeting going. There you go.
Okay. First, I want to thank Dave Folsom and Pearl TV for tonight's presentation. Greatly appreciate you taking the time to do this and help our members. You know, when we were first, talking about this meeting back in December and planning it, we wanted to go beyond just the standard. I know Dave is going to discuss the standard with you tonight, but we're in the planning stages now. There's in the Boston market, and we have the opportunity now to learn from the markets that have gone before us, and the good and the bad. And also, there's been a lot of developments with the technology from the manufacturers, consumer and broadcast equipment, whether it's transmission or TVs. So Dave has put together a great presentation for us tonight with a lot of information. He's going to squeeze into our meeting time, and afterwards he will answer your questions. So if you could hold off on those questions until the very end, that would be great. That way Dave can get through all the information that he's going to provide us tonight. Before I let him get going, I just want to remind you, I believe he mentions this in his presentation, but he is the author of the very helpful host station. I love Zoom and trying to figure out where my camera is on my little laptop here. But he is the author of the host station manual, which is on version 12 at this point, and is full of lots of great information, and is available either at atsc3.org, the atsc.org website, or Pearl TV's website, and that's for free. I believe we will also be putting it on our website, so you can download it for free. So great resource that you can use after tonight to get ready for the transition. So I'm going to give the floor to Dave, and thank you very much.
Well, hello, everybody. Hopefully you can hear me okay. We're going to try to cover an awful lot tonight, and I thought it was best to give you a little bit of the overview of the technology, because you never know the audience how much they have or understand even the very basics of a new technology. So sometimes you don't want to be in a position of talking over people. So the detail takes a long time to learn because it's an incredibly complicated standard, but I'll try to give you enough to at least have an appreciation for what needs to be done, and also more importantly, where we are in the transition rollout, both on the transmission side and on the receiving side, so that you can get a feeling for how quickly this transition is going to take. Okay, oh, all right. What we're going to discuss today, I'm going to give you a quick overview of the standard. We're going to talk about market transitions, the transmission equipment that's available, consumer receivers and sales, and how's that coming, requirements for NextGen TV security, single frequency network testing, which is a big part of what one of the more exciting capabilities of NextGen television, or ATSC3. And by the way, those two terms are used interchangeably, because ATSC3 doesn't mean a lot, but at least NextGen TV speaks a little to what the technology is. Run 3 TV application framework, and we'll understand what that is once we go through it quickly, but it's the web environment that can be used in conjunction with the NextGen television transmission and the broadband delivery of NextGen TV, something you probably have not heard about yet. Okay, a quick overview of the standard. The ATSC3 NextGen standard has really 6 noteworthy features that kind of make it hopefully last longer than the ATSC1 standard lasted. First, it's evolvable, or as some people like to use the term extensible, which is not a very commonly used word, but evolvability has at least a little more meaning for most people, and that is has the ability to change without having to write a whole new standard. We can change video codecs, so we can change transmission methodologies and other key parts of the transmission standard without having to write a completely new standard. And that evolvability is very important. We'll get into a little of that. It has the ability to be transmitted over the air and over the top, or broadband delivery is sometimes called. It has enhanced picture quality. We all know that. We've all read the trades. It has immersive audio with AC4. So it has Voice Plus, which allows you to hear and controlled by the viewer. The voiceover is controllable, or the center channel, if you will, of the audio is controllable separately than the rest of the dialogue. It's particularly good in things like football games where you can't hear what the commentator is saying because the crowd noise is so loud, and you can control that. It has dynamic ranges controllable by the viewer, and it has imaging. And for you audiophiles out there that may probably know what imaging is, but imaging is that kind of movie theater experience you have where airplanes that fly over appear to be in the theater with you, over you, and things that happen below you feel like they are happening below you. It isn't just the left, right, center kind of experience. And it's more than just that it's 7 channels. It also is controlled by phase. But anyway, that being said, it's all part of the standard. It's W3C HTML5 compatible, not only for the broadcaster application, but you'll see that really the standard is HTML based, and we'll get into that a little bit. And it has content security and service protection, which requires more explanation, and we'll talk just a little about that as well. Without the underpinnings of it, really it's not one standard. You know, we talk about the ATSC3 standard, but it's really 22 individual standards that call out what the physical layer is, or what the signaling is, and again, I won't go through all of them, but it's not one document, it's 22 documents. There's 10 recommended practices for those documents, and there's 2 technical group reports. And you can download all of these free at atsc3.org, or hopefully you'll start with my host station manual, which will kind of set the stage for you, or set the dinner for you, so that you can understand why there are different standards that take up individual parts of the whole NextGen technology. It's well over 1,000 pages long, and it's growing. I mean, there's another standard added to it every year, and every one of the standards gets updated once per year. It's based in Internet Protocol and HTML transport, and I mentioned that before, and that's going to be an important part to understand as we go forward. It's UDP and multicast, which means for those who are computer wonks out there, UDP means it's unidirectional. Does not require, as TCP/IP requires, a handshake from the destination. And that's important because you'll have millions of viewers out there and you can't be getting handshakes from each one of the viewers, even if they had a connectivity back to you. So UDP is important, but it also increases the speed. And if you use it over the top, it is TCP/IP and HTTPS for broadband. So it's actually delivered as web content over broadband, and we'll get into that as well. Uses CFDM modulation and LDCP coding for forward error correction. That's makes it a very, very robust signal. We can send 4 different modulation and coding schemes at one time, which means, well, we'll get into that. It's hard to explain in a single sentence, but it allows a tremendous amount of flexibility to the broadcaster. It has requirements for content and service security, and content service security, simply stated, is content security is encryption. So you can encrypt the content like video and audio, and the service security make sure that the viewer can make sure that what they're watching is really from the broadcaster. And you say, well, gee, that seems to be over the top. Well, no, it isn't. If you think about it, when you get on a website, chances are, if you look up in the upper left-hand corner of your web browser, the website you're on usually says HTTPS, and that S stands for a certification from that between your computer and the source website to make sure that there was no man in the middle in between that has hijacked that content. And essentially, it does the exact same thing. So that's service security. Built-in interactive application capabilities, we'll get to that, and advanced and more efficient video and audio capabilities. It's important to understand noise threshold, and I promise not to get too deep into this, but this is one thing that is so misquoted and so misunderstood. I thought I'd throw this in. If this is a curve that shows the inverse square curve that you would find of any radiation of any electromagnetic wave, be it light, be it RF, doesn't matter. The field strength drops by the square of the distance. It's really that simple. And there's a noise floor, and that noise floor exists in any electromagnetic radiation system, and it's measurable at any given frequency, but we'll call that red line. So the difference between the signal level that the receiver gets and that noise floor that's relatively constant, it has a ratio. There's a ratio of one amplitude to the other. If the ratio is large, the signal strength is strong compared to the fixed signal and noise. If the ratio is small, meaning there's a small difference between the two, then the number becomes smaller. So the further the distance from the transmission site, the lower the signal to noise is. Now, receivers only have the capability at a given modulation encoding type to pick up a certain signal and noise, and then they fall off the edge. They can't pick up if it gets any lower. If the signal and noise gets any lower than that, then what happens is the receiver it falls apart. It can't pick up the signal anymore. Now, in ATSC1, where you watch probably every night when you watch television, that signal and noise ratio, where it kind of falls off the edge of the cliff, if you will, is about 15.5 dB on an average. And I know that number because it's the number that was kind of established when the ATSC1 standard was put together is kind of a critical point, and the FCC has adopted it as a means or a level at which general transmission systems are measured. So we can say that the fixed modulation encoding provided by ATSC1, the signal and noise is 15 dB. But wouldn't it be nice if you could control where you were on that curve by just adjusting the modulation encoding to adapt to whatever your need is? If you had all your viewers were very close to you, then maybe you might want to trade some of that signal and noise capability for more bandwidth. And I'll show you that curve in a minute. Or if you're trying to reach a mobile audience and they're driving under bridges or they're parking their cars in garages, they want to be able to pick up your signal, then you want it to operate at a much lower signal to noise ratio threshold. So this threshold curve is really very critical for understanding how the basic modulation encoding in ATSC3 works. And it's known as the Shannon limit. Shannon was a professor and mathematician back in the late 40s who calculated and knew nothing about television and knew nothing about anything other than he was working on communications theory at MIT, and he was trying to figure out in any given system what could be the maximum amount of data that could be passed through that system, that channel as he would call it. And he came up with a formula, and that formula has been accepted since then, known as the Shannon limit formula, which determines how much bandwidth can be traded for how much signal to noise. And you can see that in the middle of this graph, ATSC1 isn't even close to the Shannon limit, or in other words, it does pretty good, but if you notice, it's a fixed dot. There's only one dot, and that's the one modulation encoding that you have in NextGen in ATSC1, and therefore it's only one spot on the curve. But with ATSC3, you can pick any of those dots you see just below the Shannon limit curve, depending on the modulation encoding parameters you pick. Modulation being the CFDM QAM that you pick, and the coding being the amount of forward error correction that you select. And there's over 10,000 usable combinations, two knobs, if you will. One is forward error correction, the other one is modulation. So you can pick whatever one you want. Now, even better, you can transmit 4 different systems at one time. They're referred to as physical layer pipes, and every broadcaster can transmit up to 4 simultaneously. So you can have some services that are aimed at a mobile audience, and you can have other services aimed at maybe 4K of video, let's say. So this ability to be able to transmit multiple transmission thresholds simultaneously is really a very, very powerful capability. NextGen TV and the Matroyska, I'm probably killing this this pronunciation, but Matroyska doll, I guess is how you pronounce it. And what does NextGen TV have with a Matroyska doll? Some people call them babushka dolls, but I was corrected by a Russian friend who told me that that is not correct. This is a 7 doll version of the Matroyska doll, and one doll fits inside the other if you've never seen these before, until you only have one doll, which is the larger doll. And that's indeed exactly how the structure of ATSC3 works. And I like this kind of analogy because it becomes easier to understand. There are 7 layers in the transmission standard, all the way from the physical layer at the bottom, which is the actual TV transmitter, if you will. And on top of that is a data link that has been put inside of that physical layer. And then there's the network layer, which is put inside the data link layer. And then a transport layer, which is put inside that layer. And then on up through the application layer, which would be the video and audio that you would be normally watching on television. Each of those is, you see, we start with bits. The frames are put inside of the data link frames are put inside of those. Packets are put inside of those. Segments are put inside of those. And then the data from the session, presentation, and application are put in each. And there's a presentation header, a session header. That's what the SH, TH, NH, and DH stand for. Those are headers that tell that layer what is put into it from the layer before. And this is known as an abstraction layer, meaning anything that happens in that layer doesn't impact it only impacts the layer before. It has no impact on any of the rest of it. You say, well, gee, boy, that's kind of convoluted. Why do you go to that much trouble? That allows evolvability. It allows you to change the content of one layer, like let's say the video codec, without the rest of the layers caring. The rest of the layers don't care what the codec is. If you're using TCP IP for delivery instead of UDP, that's on the transport layer level. And the transport layer, if you made that change, the layers before, the session, the presentation, and application layer don't care. You don't have to make any change. So that makes this allow you to use the standard in more than one transmission or delivery methodology. I'm not going to go through this, but this is really the full stack. You'll notice it's 7 layers tall, and the pink is the most important, or the salmon color, which is the middle, that shows MMT signaling, route signaling, and announcement. And you'll see LLS and SLT. That's known as signaling. And think of it as road signs. They're road signs that tell the receiver what's on that layer and where it can find things. Like the LLS, for example, is a link layer, and it contains within it a means by which you can. I said link layer. I'm sorry. It's the lower layer, and it points to the SLT, and the SLT points to a thing called the SLS, and the SLS is the directory, if you will, that points to where things are, video, audio, where the application resides. And all of these addresses are web addresses. So think of your television set as a big web browser, if you will. In the web browser, you don't control. The control of that web browser, you can't type into it and say, I want to go here, there, wherever. The signaling inside of this tells the web browser in ATSC3 where these various components are and what to display. So if you select a different service, you can carry multiple services within a channel. That service is found inside the transmission, inside these layers. It points to it through the signaling. The receiver knows where to find it, and then it displays it. A little hard concept to get your head around, but I try to do this quickly to have you have an appreciation for the structure of how this works. In the transmission, I try to simplify it. This is a transmission chain that you would buy if you were going to transmit ATSC3. Each of these boxes, particularly the ones at the top row, that starts with encoders, route, NRT, and broadcast gateway, are really computers. They're servers, and they're just off-the-shelf Dell or HP Enterprises servers, very powerful servers, and they're running software. And the software in the encoder section will have encoder software running it, and the route NRT signaling will have a specific kind of software running that deals with multiplexing the signals together and putting the signaling in that we showed you. And in the last one, the broadcast gateway, that does the difficult job of placing the multiplex stream on top of the physical layer pipes that I mentioned, and also tells the exciter what to do. So I start by showing a compression, which is where the encoding takes place. Then I show multiplexing, which is the next transport encoding and multiplexing. It's also where you add things like non-real-time files, but you multiplex all the signals together, data signals, and then at the end you lay it in a link, what's called the link layer, and the link layer make sure that those pieces are put together and are organized in such a way that the receiver can put them back together and then demultiplex them to decode them to show them on the air and show them on your display, sorry. And then the output of that then goes to the exciter in the at the transmitter, and it's transmitted on the over the air. Okay, the transmission through 12/31 of this year, we've had about 51 markets get on the air. It's a little difficult to tell you how many markets because it depends on whether you count low power transmissions or not. There's a tremendous number of low power stations on the air, but we'll get into the detail a little more in a minute. You'll notice there's more hosts than there are markets because there's a number of markets. In this case, you can do the math, 13 markets in which there are 2 hosts. And each host can handle about 5 TV stations. Some handle less, but you can actually multiplex these stations onto a single channel. And so we tend to call them services because the word channel can get confusing. What are you talking about when you say channel? it's a word that I grew up on, and you always think of a service as being a channel, but it's important, and particularly NextGen television, to think about things as services. So because they can reside, multiple services can reside on a single channel. So we have 64 hosts at the moment. There's actually more than that because it's ended on 12/31. For example, I believe it was yesterday that West Palm Beach went on, and I think in the next couple of days we'll have Charleston going on, Charleston, South Carolina. So there's a number going on almost every week. There's one or two that go on. So these numbers are already dated. One of the questions I get all the time is how many, but yeah, it's fine for UHF, but how many VHFs are out there? Well, 2 are shown here. There's actually more than 2 now. I think it's up to 4. VHF, particularly above channel 7, are fine. There's no real degradation. There's a little bit of problem on channel 6 and below. That's real channel, not display channel 6 and below, but real channel 6 and below with noise. It isn't that it doesn't work. It's just that noise floor that I show you, which is fixed, becomes higher the lower in frequency you go. And so that's a total of 263 services are on the air out of 1,800 TV stations plus. And we're reaching about 59% of US households. And that's higher now, as I mentioned, because we've had a number of stations go on the air since the closeout of this number of statistics. We have some problematic markets that we're going to focus in on this year. New York City is one of them, particularly. LA is already on. New York is problematic mainly because all the transmissions are either on Empire State Building or on World Trade. And there are lease problems with stations that are normally on World Trade from being carried on on a host station on Empire. I won't get into the details of that, but it's messy from a real estate point of view, not from a technology point of view. You'll notice Boston is one of those difficult ones. And most of these difficult ones are difficult, not because the broadcasters are being difficult, but because there isn't a lot of free spectrum. And a lot of these larger markets, the spectrum was sold off. I think, for example, in New York City, there's 13 stations as a result of the repack that are already sharing. So much of that free spectrum that is available to allow for stations to share spectrum back and forth to free up a channel to create a host station is gone. Boston is in the process right now to try to glean enough bandwidth between a number of partners so that we can get on the air. That's going on behind the scenes at the moment. And the rest of them you see there are all active and are anxious to get on. But again, it's the problems of finding sufficient bandwidth, which is holding us up. This kind of shows it kind of visually. This is a little more recent. It's not frozen at the 31st. It was actually accurate as of the last Friday. We track these statistics at Pearl. I'm sorry, this is a kind of an eye chart, but there's a Tableau, which is the software we use to do this tracking, is unfortunately picks some of these default colors, and it makes it difficult to read, and particularly in a presentation. But the short version of it is that the total number of, we believe by June of this year, it will be on the air, will be 99 million TV households will be covered with those TV stations. And out of I believe there's 120 million just over 120 million households, Nielsen households in the US. So 99 million will be covered by June of this year. The blue is, I believe, what's already on the air, already launched. Active planning is in the kind of tan brown color. And the green is upcoming shortly. They're in between being planning, and some of those have already gotten on the air. I mentioned, for example, West Palm Beach, and you'll notice West Palm Beach is in green down in the bottom, down in the Florida. You can see it's green. It's actually turned blue since yesterday. This is projections that we see through June on the year. The two graphs, one of them is full powers, and the tan is lower power or LPs. And it's difficult to add these two numbers together because it won't work, because some of them overlap, meaning that the low power is going on the air in a market that has already got a full power and vice versa. But easily we'll be covering, as I mentioned earlier, 99% of 99 million households by June or so. Transmission equipment I already mentioned. What is different from what you need for transmitting ATSC1 is mainly the encoders are quite different. They use HEVC and AC4. You'll need a route signaling device that deals with that signaling that I told you the receivers need, and also does the multiplexing of all the signals, and also a broadcast gateway. Now, those I mentioned are individual servers. They can technically all be in the same server, a very big server, but they tend to be different manufacturers, so oftentimes they're in different servers. But again, they're usually, as they call them, OTS computers, or off the shelf. The exciter is different than an ATSC1, but every exciter purchased probably in the last 5 or 6 or maybe 7 years is ATSC3 capable. It usually is just an activation of a license, because exciters are all software based as well. They're nothing more than a server. So almost every one of the boxes you're looking at here, other than the transmitter, are essentially just Linux based servers. And they have a tendency to run a virtual machine, which makes it easy for backup. So you can have backup server sitting around, and should a server die, you can take the virtual machine image and move it to another server very quickly and get back on the air very quickly. A lot of people making ATSC3 equipment. I'm not going to go through this long list, but just to show you that in this list that there are a number of folks that are focused in on ATSC3 equipment, and this list is growing daily, including the major manufacturers of receivers, which is really critical. Okay, speaking of receivers, I want to talk to you about chip development, which for one main reason, and that's to kind of let you understand how consumer manufacturers work. The chip on the left is made by Sony, and it's a receiver, RF receiver tuner module. And the chip itself, as you can see, you can fit maybe 5 or 6 of them on a penny. So it's very tiny. But it's also an ATSC1 tuner. It's an ATSC3 tuner, but it's an ATSC1 tuner as well. And that's going to be important for understanding a point I'm going to make in a minute. The chip to the right of that is a demultiplexer chip. And it takes the signal, the data that comes out of the tuner chip, and does the opposite of what the multiplex box that I showed you in the block diagram earlier. So that what comes out of that chip is an IP stream, just like an IP stream that would come out of an internet cable box into your computer. And so the next chip I don't bother to show is what's called a system on a chip, which is really nothing more than a dedicated computer chip, which would decode the video and audio and create the display for your TV set. And it does a whole bunch of other things, like allow you to watch Netflix and all the other stuff you do with your TV set beyond watch over-the-air television. But that system on the SoC chip's been around for a long time, so I didn't bother showing that. Again, this is the LG tuner chip. You can see that's a little larger, but still very small chip. But it's also ATSC1 and ATSC3 in the same chip tuner. Okay, here are the 4 manufacturers of consumer receivers: Samsung, LG, and Sony. I should mention that all Sony TV sets are NextGen. If you go out and buy the Sony TV tomorrow, it'll be a NextGen receiver. They don't sell ones that aren't NextGen capable. They're also ATSC1 capable, all of these receivers at the same time. And it's invisible to the viewer which one they're on, other than looking at the guide, they'll be able to tell. Hisense, which is a name for a next tier. The premier tier tends to be the Sony, LG, and Samsung. The next tier is Hisense. They've joined the marketplace this year. And this shows the modulated chips they're using. You see that Sony, the modulated chip, is very popular. And the SoCs they use are also shown as well. MediaTek is the Taiwanese company. LG and Samsung, of course, are Korean. And Sony, of course, is Japan and the US. There's over 100 models that were introduced in 2021. Many of them are still available because the 2022 sets, although they were introduced at the CES show in January, don't really make it into the marketplace till April or so. So the 2022 sets have been announced, but they'll overlap with the 2021. So there'll be about 50 of those that have been announced. New models added to the 100 that are already available. So for a while, there'll be about 150, but some will drop out because they're replacing older models. So there'll be about 130, maybe by the end of the year, net different models, and they're all ATSC1 and ATSC3 capable. They're all smart TV sets, meaning they all have the ability to do other things like watch over the top and do all kinds of other stuff that smart TVs are capable. So having them connected to the internet is to your advantage, and which will be important for a while. There's also a number of set-top boxes coming as well, and those set-top boxes are being held up a little bit right now because of the worldwide chip shortage. They don't stand in the same line as the major manufacturers of receivers, of course. But DigiCap, which is a Korean company, CommScope, which is a US company, which supplies them for a over-the-air service called Avoca. They're available. Will be shortly, if they're not available now. Tableau, another company that's well-known, making set-top boxes, and Zinwell also will have a set-top box for ATSC3 this year. They'll be in the $100 to $200 price range. I mentioned the household penetration, and what's also important is what is the rate in which the TV sets will be sold. So the black line is the penetration of households with a signal. The red line is the penetration of this households with receivers. And of course, you ultimately would like to have the receivers and the signals be equal. But in the formative years, people take a while to buy the new technology because they have TV sets already in their homes. So we've kind of laid this out through 2022. You'll notice that we're by the end of this year, we'll probably have about 7 million sets out there, 8 million. But at the same time, we'll be well over 80 million households that we've reached, if you include the LPs. If you don't include the LPs, it'll be something less than 80 million households. So, but I do include the LPs because the LPs can get coverages. Remember, I told you can dial a signal and noise. You can get coverages with LPs that equal the coverage of an full power just by trading a little bit of the bandwidth available or payload available for a better coverage. Interesting. That's why there's so many LPs going on the air right now, if you were wondering. Okay, let's talk quickly about security, and I want to move along a little more quickly. I'm talking too much. They leave enough time at the end here for some questions. Quickly spoken, at the bottom, if you notice, there's a block that says encapsulator, scheduler, and exciter. That receives signals from the middle box called the packager scrambler. And that's where the encoder is. And you'll see the video coming in from a camera that says encoded content. There's two things that need to be added to the signal. One is that certification to ensure that we know that the signal is the signal that is being transmitted from the broadcaster. that nobody's gotten in the middle to interrupt it or is spoofing. Because remember, you may be receiving a signal via over the top as well. And you don't want man-in-the-middle attacks where people hijack your IP address and essentially start transmitting porn or stuff that's embarrassing or is not appropriate. So you want to have some way of making sure the receiver can be sure that the signal is what it says it is. And that's done through a certification authority that's shown on the left-hand branch there. In the middle, you'll notice there's an encryption system, key server, which provides a key to the encoder. And then encoder that's in your transmission chain can scramble or encrypt is the appropriate word, the signal in such a way as with an enormous key, 256-bit key, that would make it nearly impossible for somebody to decrypt it. And it's a rotating key. It's constantly changing. So it would be very difficult for somebody to take that content and spread it out over the internet, for example. The networks are going to require this. That's why it's in there. The licenses that are required to decrypt the signal are in the TV set. They come from the factory that way. And so the receiver can decrypt it and display, but there's no outputs in the receiver to allow you to capture the content in any way. Again, it's to prevent pirating, piracy, and if this sounds maybe a bit dramatic, when you watch Netflix every night, or you watch Prime, or any of the other over-the-air systems, virtually every one of those are encrypted. You don't know it's completely invisible to you. The fact that it's encrypted, you don't see it. And if you watch a DVD or a Blu-ray more accurately, that's encrypted. It has been encrypted since day one. And the encryption key is actually inside the DVD player. So again, or a Blu-ray player. So encrypting content is not a new concept, and it's included in the standard. Single frequency network, quickly, we've done extensive testing of single frequency network capability. It allows you to transmit on your same channel in your coverage area. So this is Phoenix. And if you'll notice, there's a green, it's hard to, probably difficult to see on a small screen, but there's a green circle, which is a coverage for a KASW, which is a station in Phoenix. We put up another transmitter in Shaw Butte, which is north of the city of Phoenix, on the same channel, transmitting exactly the same thing. Now, normally that would create an enormous amount of ghosting, but we time the two such that the ghosting is within the capture capability of the receiver. So the receiver actually takes both signals and adds the primary signal and the ghost signal together. And as a result, end up with a much stronger signal within that coverage area. So you can see within your own coverage area, you can fool that signal and noise curve that I showed you that drops at the inverse square of the distance from the transmission by putting up other transmissions. Shown in the same picture is one in red and one in purple. Those are two other transmitters that could be set up on the same transmitting frequency, transmit the same signal, and again, increase the signal level so that we could have a very, very good signal noise with good data bandwidths, but at the same time, fool the signal and noise issue that I mentioned before regarding the Shannon curve and the ability to be able to transmit to great distances and still have great bandwidths. I won't go through all this, but in this particular test, we were able to get absolutely error-free reception in 80% of the sites without one data bit being missing. The service margin for 40 of the sites, and we did test in 40 sites, improved by about 6 dB at 30 feet and 10 dB at 12 feet, which is really important because not many people have receiving antennas at 30 feet. But that kind of improvement at 12 feet, which is kind of not a bad height for, let's say, a second floor of a home with a inside antenna, is really a critical number. And service availability improved as well, which was really very critical. In other words, places that couldn't get it at all suddenly were able to receive it and get a receivable signal. If you want to read more about that test, because it's too much to give in such a short time, it's available at pearltv.com, station resources, and it's free. It's a 43-page report, and please download it and read it, and it'll give you more detail about how we went about doing the testing. And by the way, that SFN is still up and running and working just fine. Thank you. Okay, I mentioned that you could do run an application within ATSC3. It's part of the standard. It uses regular HTML code. If you have know anything about creating a website, you can provide an application in ATSC3, and you're allowed 3 layers. You're allowed the background layer, which is the transmission you normally transmit. You're allowed a see-through layer, if you will, which controls how much of the background gets seen, and you're allowed a composited display layer. In the right-hand side, you notice you can squeeze the signal down. That's one of the capabilities within ATSC3. You can squeeze and put it anywhere you want. The normal broadcast, I'll show you a little bit of that, and then you can overlay it with normal web content, and we'll see how that might work. We at Pearl created an abstraction layer to make it easier for the broadcaster to not have to deal with differences between the browser capability of receivers. And it's called Run3TV. It's free. It's our gift to broadcasters. And it provides them, again, an abstraction layer, so the people who are creating web content don't have to think about whether it's going to run on a Samsung or an LG or Hisense or whatever. And it becomes part of the application, and it's sent along with it and allows you to do a lot of things that would be difficult for broadcasters to deal with, depending on who necessarily was viewing it. The back page, if you will, I tried to show you 3 pages in one, is what would happen when you turn the TV set on and you're looking at whatever's being brought by the broadcaster in the background, and this call to action Run3TV button will come out, and it kind of focuses the viewer on using the arrow keys on their remote control. If they push the right blue one, which they're being kind of hinted to do, what will come out are the next screen up in these 3 layers, which will show the menus that are available. And you can have as many nested menus as you want. And those menus can go to other submenus, and you can navigate up and down using the buttons on your remote control. And the third one shows that let's say you get to whatever layer you want in the menu system, you can also show icons of, let's say, video content. And that video content can be delivered over the air, or the video content can be delivered over the top, like maybe what the weather is, or a newscast, or whatever. And you'll notice that the picture has been squeezed behind, just to show you that what the video is going on. If it was a football game or whatever, you would see it squeezed down. You can squeeze it down, or you can just have these come out as an overlay. That's really up to you. This is what it would look like in a full screen kind of mode. Obviously, the nightly news, and somebody operating the controls has whipped out and pushed the button, and the first menu came out. If they push the button again, the second menu would come down, and you can then navigate up and down and select whatever you want. For example, what you missed, Law and Order, True Crime season finale on Hulu. You could click down and click on it and go to Hulu if you wanted, or you could go to your own website. It's whatever you program in it to do, and it's not difficult to program. This is another one that shows much more simply a series of news clips that you can select, and you already are putting news clips up on your website, so those news clips are already readily available. All you need to do is put the icon up there. It takes very, very little additional effort to provide it, as this means. And you'll notice again, in this case, it's overlaying the picture behind as opposed to squeezing it over, but you can control that. This is other ways that web content, it can do paper clips or promos or call to actions for getting more information. If you'll notice at the bottom, there's 3 screens here, each showing different. One is for getting more information about a movie, a Perry movie. There's a BMW ad. You can get more information about where you can find the BMWs, I guess. And another one is a Ford ad, and you could click down and select to get more information. And it's a way of creating inventory without necessarily what's playing in the background can either come via your application, or it can be something that's on the screen and that's coordinated with your regular normal broadcast. Okay, broadband delivery. When we looked at this stack that I showed you earlier, you'll notice that on the left-hand side of the stack, at the bottom, it says broadcast. That's the 7 layers that are used for broadcast. On the right, it says broadband. And if you'll notice where they're different, it starts at the HTTP layer. Instead of the transport being route, it's HTTP. And above that, it's the same. So you can transmit, and remember I told you, each of them are abstraction layers. So the upper layers have no idea how they're being transported. So if you want to transport your content via HTTP, you can. That's really kind of up to you. Or you can go over the air, which is the left-hand column. And it's simpler to do than this, than it's shown in this graph, but you have to understand the structure behind the scenes. Here's again, that same drawing I showed you before. The only thing I did is I moved the transmitter and exciter to the top of the screen, but the rest of the drawing is the same. It shows the same 4 major elements of the interface to the other stations that you're helping, and the encoders, the guide builder / multiplex, and the last is the broadcast gateway. If you want to carry that signal or another signal over the top at the same time, you can add to the number of services you carry on the air, some of which will be over the air, and some of them can be over the top. The viewer will see them in their guide as being the same. The receiver receives the IP signal and just sees it as an IP address. It doesn't care where it got it, whether it got it over the air or it got it over the top, as long as you have it connected to broadband internet connectivity. And so this is what you need to add. In this particular drawing, you'll notice you had to add a little bit of addition to the guide builder, because there's a little more signaling involved. So that really indicates the added signaling is needed for the service layer and SLS that's required for the over-the-air that goes over the air. And the requirement for sending a over-the-top signal or broadband delivered signal has to be that the signaling must go over the air. And you say, well, why is that? Well, because you only have the rights, most TV stations only have the rights to deliver content to their own market. They cannot transmit that content unless they created it themselves, but if for their networks or their syndicated content, or if a public station came from PBS, they're given rights to that market only. So the way we control the signal only going to that particular market is that all the signaling telling the receiver where to find the services goes over the air. And that way, as long as you're in the coverage area of the transmission, it'll know to find it over the top and where to find it. At the bottom in that red dotted line, you'll notice there's another encoder, which is required to encode the video and audio, and another thing called an origin server. And an origin server provides the IP addressing and the handshaking that's required in TCP/IP. That also needs to go to a CDN like an Akamai or other. There's hundreds of CDNs available, because you're going to be transmitting that TCP/IP signal to hundreds or thousands, or in the case of like in New York City, maybe millions of receivers. So you have to be able to have a server that's capable of serving up that many different sources simultaneously. And the CDN is set up to do that. And that goes to the broadband connected TV set. It receives the signaling over the air. It's shown in that little antenna, and that broadband receiver or connected receiver you see in the lower right-hand corner is picking up the over-the-air signaling, and at the same time, it's getting the actual signal itself or the service itself over the top. Wow, that was too much in too short a time. I'm going to open it up to questions. I went a little over, but I wanted to be as clear as I could with as much material as I packed into this. I'll leave it open for questions if anybody has any questions.
Great job, Dave. Great job.
Thank you.
Dave, Dan Brown here again.
Yeah.
Can you discuss a little bit about EAS delivery and capability on the standard?
Yeah, EAS is part of the standard, and it's there in a couple of different ways. One, there's a thing called a wake-up bit, which is at the very beginning, at the very lowest level in that stack I showed you, the 7-layer stack. And that wake-up bit, which comes every 5 seconds or so, has the ability to turn the TV set on if the TV set manufacturer chooses to do so, and which kind of makes sure that even if the TV set is shut off, that the person, the viewer, realizes something's happened. Then at the same time, there's that part of that signaling allows for a delivery of an advanced alerting system, and that can be video, it can be text that runs across the bottom of the screen, it can be an audio like a WAV file, or it can be a web address that it forces the receiver to. And remember I told you that the receiver doesn't care where it gets its content as long as it's HTTP content, and it has an IP address to go to. So the EA message may only send the TV set automatically to that EA message. It could be I don't know, an Amber Alert, or it could be a tornado warning, or who knows what. Now, the part that doesn't exist, the technology exists in the receiver, it exists in the transmission, but unfortunately there isn't the organization at the local level in many states. And that's the part that needs to get organized. And there's some work afoot in a thing called AWARN, which is a group of folks, volunteers that have gotten together to try to organize these various systems that are, there's 50 states and there's probably 100 different emergency alerting systems, or greater than that, beyond EAS. EAS is only allows for the president to talk to you when there's a national emergency. We need all of those other kinds of, weather emergencies, Amber Alerts, all those other emergencies, which need to come across that system as well. And that's the part that's kind of disorganized and needs some unity. And the folks at AWARN are kind of working on making that interface between these disparate systems and what could be a single delivery system with ATSC3.
Okay, so you're saying that the audio and text crawl will occur in the viewer's set now as compared to originating in television master control?
The answer is it can. Remember, when you're dealing with a TV set, stop thinking about it as a transmission that we send from a mass control. Think about it as a virtual environment in which you could send the TV set to a website, or you could send it to a national, and that's kind of all invisible to the viewer. So I want to make sure you understand that all of the things you can do now in band. That it won't take any of that away. But if you want and you choose, and the FCC allows you to do it, and they are holding, I think you've probably noticed there's been some dockets that have come out in the last few weeks about revamping the emergency alerting system, because they're also aware. Pearl has been very clear with the FCC. We're an advocacy group, and one of the things we do is make sure the FCC is brought up to date on what the capabilities are. So they know about AWARN, they know about the fact that the whole emergency alerting system requires revamping to enable the capabilities of the next generation TV sets.
Great, thank you very much.
Yep. Other questions?
I have one.
Yep.
Actually, I have a couple. First of all, I'm John Schulberg. I'm coming to you from Dallas.
Yeah, good.
And with your involvement in Pearl, you no doubt had a chance to rub elbows with an old friend of mine by the name of Bob Chase.
Yeah, Sure
So
do.
Bob's an old friend, great guy.
Yep.
I just wanted to have say hello to him through you via that. Now,
I sure will.
couple questions I have. Is it, say for example, you're a TV station that just wants to do more channels.
Yes,
So now I have the capability with ATSC 3.0 to carry more data and more bandwidth. What is the payload limitation of the
Okay.
ATSC 3.0 stream?
yeah, good question. The lowest payload practical in that chart I showed you, the Shannon Limit chart, is about 4 megabits per second, which is an incredibly robust signal that would go out hundreds of miles, go out to the radio horizon. The highest you could go do is about 55 megabits per second. That's the highest point on the curve. And at 55 megabits a second, then the signal and noise would probably be on the order of 35 dB, 32 dB, somewhere like that, which means that transmission would only go out maybe 20 or 30 miles. But on the positive side, you could build a SFN, and the SFN could take it out to your normal coverage area.
Right.
And so you have the full payload. So it's a difficult question to answer because you're given all the tools to have the coverage you have now, if you wish, with multiple transmitters, all on the same frequency, and at the same time take advantage of transmitting 55 megabits per second.
Okay.
Did I answer your question?
Yeah, thank you. And if you had a broadcaster that was primarily interested in, because I still think the killer app for 3.0 is going to be video, going to be more TV channels. And we've already proved that with ATSC 1, that the sub channels are very lucrative. And now there could be other things that 3 brings to us. But if I had, prior to going to my exciter, I have this bit stream, this data stream, if you will, and maybe that's the wrong word to use, but this data heading into my exciter, if I took that off and sent it to a browser capable of decoding it, would I then be able to go ahead and have my phone browser use my AT&T cell site to log into an IP address that the station might have, that I could then go ahead and watch anything on that stream that the TV station created before it hit the exciter?
The short answer to the question is, and I'm not being a wise guy here, but the technology allows for it. What doesn't allow for what you're talking about is rights. And when we're dealing with content, unless you own the content, you own it.
Right.
Most people have the rights to content only.
Sure.
And therefore, for example, the NFL or Major League Baseball, and I'm not a sports fan, but all the sports, the rights are divvied out individually for individual media. So if you have the rights for over the air and broadcast in Boston, you will not have the rights. I can tell you for sure, you will not have the rights to the mobile on any of the mobile carriers. For that matter, you don't have any internet rights either.
So it's a legal programming limitation.
Yeah, the rights. And now that being said, there's also a positive side of that. And the positive side is, if you are our owner of content, which many broadcasters, particularly in big cities like Boston, are, then you got a leg up because you can do anything you want with that content.
Hello, Bozo.
Yeah, so if you've got news or you carry sports or you create your own entertainment content, God love you, you have the ability to do whatever you want with it. So you have an advantage because you have a delivery methodology that supports multiple ways of delivering that content.
Yeah. Thank you. You've answered that both questions clearly.
Yep. So it's a good news, bad news story.
And I thank you to you and the Pearl and all the other folks that are working to bring this to fruition. There's a lot of work involved here, a lot of very technical matters. And you guys have really, really been putting it to the grindstone here to get this taken care of. And broadcasting needs this. It needs
thank you.
1.0.
We
hats off to all of you.
Thank you. I'll tell you one more story, which is true. For the last 20 plus years, up until 2015, I was, for 24 years, I think I was the chief technology officer for Raycom, and that was hard work. I mean, it really was. But I can tell you that the 5 years since I've retired, 6 years, whatever it is. I've worked 3 times harder, and I'm supposedly retired. But it's just not just me. You know, Pearl, which is an advocacy group and a technology, we do technology research for our 9 owner companies, the companies like Hearst and Cox, and but we also do it for the 5 networks. 5 networks are part of the Pearl Network Consortia. I went over this slide at the beginning, which explained that. It's in, when you download these slides, if you do, you can read the detail of that. I didn't want to spend a lot of time with it to find out who Pearl is and what we do. We don't make a product. We're Switzerland. We work with all manufacturers of TV sets and equipment, and we don't judge anything. We support and try to do testing, independent testing. We do advocacy of broadcasters' point of view. We make sure that the standards include those capabilities we think are important to keep the business healthy. So that's really what Pearl is all about. It's exciting work. It's fun. I do it because it's a lot of fun. And I also wrote the host station manual because as the time has gone on, I'm getting older, and there's no way I can inject this into people's arms very easily. So I put together the host station manual, which is a terrible name for it, but point being is it gives you all the information you need to stand up a NextGen TV station. And it includes every bit of hard knocks and bloodletting that we did along the way, so that you don't make the same mistakes we made and along the way. And we had a lot more positive things happen than negative. Don't misunderstand me, but it's been a slog because it's a very difficult standard, and you make something very, very capable and very flexible, it becomes very difficult to understand, and it is difficult. So I try to write it in a way to make it easier for people to absorb, and I learn every day more and more about it. And I've been at it for, well, before I left Raycom. So since 2013, I think, is when I started with ATSC3.
So it contains every bit that'll bite.
Every bit that'll bite. But the simple way to think about it, so you don't get wrapped around the hub, is it's an IP stream.
Yep.
Like the IP stream you get to your computer every day or your cell phone. And that IP stream can carry all kinds of stuff. Media, it can carry data, it can carry just about anything you can imagine that data can carry. And the TV set has been designed in such a way to allow you to display it or make use of it or to change it. And the broadcaster is given the ability to be able to feed into that IP stream what appears to be ways to keep their business going. So long story short, there's a lot of capabilities, and it's very, very flexible.
Yeah, and how are you contending with the back channel information? How well are the stations contending with the back channel of information coming from the viewers?
It's not as difficult as you might think. At first we got all kind of wrapped up in that. So, oh my goodness. Well, think about this a minute. Every ATSC3 set is a smart TV. Every one, without exception. That means what happens when you take that smart TV out of a box? I don't know if you've ever got a new one. Took it out of the box.
Yep.
When you connect it to the power and it turn it on, what is the first thing it does? It drives you nuts and tells you, please connect this to the IP stream.
Right.
Please connect it to your internet. It'll ask you, and even if you go past that and try to go watch a TV station, the first thing it does is it pops up that screen again saying, please connect this. And the reason they're doing that is because they're selling time on that opening screen to the people who are on that screen, like Netflix and Prime and all that. They pay big money to be on that screen. And they also want to be able to send updates to your TV set. And if you don't connect it to an IP stream, then you can't get the updates. My point being is you have already a back channel. The back channel is connected to your TV.
But
and indeed, yeah.
But how well are the stations adapting to the fact that they'll have this fire hose of data coming in?
Extremely well. I'll give you one little hint, and it's too long an explanation to get on this short call.
I'm glad to hear this.
But one little hint is I mentioned the Run3 TV application. one of the things that 13 TV gives to the broadcaster is data back to their in real time about what is being watched. I'll leave
Oh,
it at
news
that.
directors are gonna love that.
Maybe. And by the way, it's anonymous data. I mean, you don't know that it's Dave Folsom at the corner of 5th and Main. Yeah, but you do know that a Sony TV set is now watching, and we have the ability, if the broadcaster chooses, to see that data in real time.
Yeah, thank you.
By the way, if you hadn't guessed, the TV set manufacturers have been doing this for years. That's one of the reasons they want you to connect it to the internet, because they want to see what the hell you're watching, because they sell that data to the various, Coca-Cola or Pepsi or whoever. So they've been doing that for years. So that's nothing. It should be nothing new. Any other questions?
Just one quick one, Dave. How is this going to land at the cable head end?
Cable head end, we're working with I call them the 3 C's. The three C's are Comcast, Charter. They call themselves Spectrum too, but it's Charter, and Cox. Those are the big 3 MVPDs. There's many other MVPDs, but those are the big 3. They have 70% of the US households, I think. And we're working with them, and Pearl is, and remember I told you we're Switzerland, so we don't take a point of view, or we don't gang up on them or anything like that. So they like working with us, and we act as a buffer between them and the networks and all of that. So we've worked out a technical means by which we can deliver the signal to them. We worked with a couple of manufacturers to build IRDs for them to receive the signal over the air. And we think we've come up with a mechanism to deliver the signal via fiber, which is the way many of you deliver your signal to MVPDs now. So we're working behind the scenes on that. And what they're really interested in is the business model. They know that we're working in an IP stream, and 2 of the manufacturers, Charter, no, all 3 are now, Charter, Comcast, and Cox, all are moving from their traditional QAM systems over to IP delivery systems. So we have a lot to share back and forth. And, retrans is going away. I mean, ultimately, it's going to hit some point where the model is going to have to change. Retrans revenues are already on the decline. And so they know that, we know that. And so it's time for us to come up with a different model in which we both can benefit. Any questions?
Hey, Dave, what is your real world experience from RF delivery standpoint, either at transmitter sites or, more importantly, in the field, specifically with multipath or other challenges to reception, reality versus theoretical?
It's actually much better than theoretical, as it's turned out, because the theoretical was very conservative, the laboratory testing, and it's turned out to be about 6 dB better than what the theory said. You can see some of that in that if you download that test document on SFNs. CFDM, which is the same modulation system that's used in your cell phone, likes ghosting. Because it can add the signals together. I mentioned that earlier in an SFN. So multipath is not as big a problem for CFDM as you might believe. If it gets too bad, if the ghosting really gets horrendous, then of course it's just like any other modulation system, it breaks down. But most ghosting is relatively, the difference in delivery times are relatively small, under 10 microseconds, let's say, 10 millionths of a second. And those kind of ghosts, the CFDM really likes. So I would say the real world has shown us that the receivability of ATSC3 is much better by a factor of about 6 dB than ATSC1.
Thank you
But
very much.
you can get some empirical evidence of that. You can get some empirical evidence of that in the download that I mentioned
Yeah.
before this event testing. I will mention one other thing, that Sony Corporation has just released, well, they've released a couple of papers. Frankly, I don't have the links ready, but one of them is for their loop chip, their receiving chip. They have a special chip that they've come up with that has 4 tuners in it and can receive 4 signals at one time. And you say, well, that's interesting, but why? Well, the interesting part of it is you can program the chip such that you can have 4, let's say in an automobile, you can have 4 antennas, one on each fender, let's say. You know, it's hidden. You'll be in the plastic inside the grill or something. You'll have 4 antennas placed in as far away from each other as you can get them on your automobile, let's say. And each one of them would feed the tuner. And just like you have, you use this with, let's say, wireless mics with diversity receivers. This is actually 4 diversity receivers, and it picks up the signal. And instead of the receiver voting on, I like that signal better than this signal, which is how most diversity works, these take all 4 signals and add them together. So as one fades out, the other one is still there, and so on. CFDM doesn't mind doing that, and it's fairly easy technology to do within the CFDM signal. And so ghosting is actually not a negative when it comes to CFDM. Thank goodness, most cell phones wouldn't work.
Yeah. Have you seen any television sets that actually have 2 antenna inputs?
No.
Okay, very good. Yeah,
No, but then again, I've never seen a receiver that had more than 1 tuner chip. So
yeah.
as long as, and now I will say that one of the boxes that I showed you there, actually 2 of the boxes I showed you actually have multiple receivers in them. The HD Home Run, for example, has 4 receivers in it, and can, with one single antenna, can pick up 4 different signals at one time. So I think the Tableau also has 4 receivers in it. So that is very possible. It has a single antenna input, but it has 4. But this diversity system I was talking about, that would have 4 antenna inputs, because again, it requires 4 antennas.
Right. All right. Thank you. Thank you, Dave.
Yep. Other questions? I'll have you know this is only water. There's no Russian vodka in it.
Any other questions? Otherwise, we're going to wrap it up for tonight.
Yeah, I'm sorry I went a little long, but it's difficult to pack so much information into such a short time.
Not at all. It was.
Please
very
don't
thorough and
apologize.
It was a great presentation, Dave.
Thank you.
Well,
Yeah, thanks for
you
the
Thank you for doing it.
Yeah.
It was worthwhile learning.
thanks for the long distance invitation too.
Oh, my pleasure. And I'll end this with a not so. Please download this if you and again, it's free. Anything I didn't include is included in that, and I'm working on version 13 already. So, but it's well worth perusing through. You don't have to read the whole thing. You can read the part that interests you, and there's a lot to be learned in there.
All right. Great. Thanks very much, Dave.
Thank you,
Thank you,
David.
David.
And,
Thanks,
congratulations to
Thank you,
Cheryl
Dave.
again.
My pleasure. Anytime.
Make
Thank you
so much.
Okay, very good.
Good night, all. Thank you.
Yeah,
Night.
good
Good night.
night, and watch your email for next month's meeting. Thank you. Good night.
Night.
Good night.